Welcome to today's lesson on kinematics of motion in one dimension. First, let's do a quick recap of the previous lesson on measurements and unit conversions, and why precision is vital in scientific endeavors. I am Dr. Moses and Tom's virtual teaching assistant. In the realm of unit conversions, it's easy to make mistakes. Remember to square or cube units for area and volume, avoid inverting conversion factors, and always check if your answer makes sense. Ask yourself, is this reasonable? To ensure accuracy, precision matters. Significant figures are essential in showing the precision of measurements. While accuracy refers to closeness to the true value, precision is about the consistency of measurements. Understanding these concepts is crucial for scientific accuracy. Let's explore the rules of significant figures. All non-zero digits are significant. Zeros between non-zeros are significant, but leading zeros are not. Trailing zeros after a decimal are significant, while those without a decimal are ambiguous. Use scientific notation to clear up any confusion. Precision in measurements is not just a scientific concern, it impacts various fields. In medicine, drug dosages must be precise. Engineering requires accurate material stress calculations. Cooking involves recipe scaling and conversions, and space navigation relies on precise fuel calculations. As we wrap up, remember these key takeaways. Units are critical to prevent costly mistakes. Dimensional analysis is your best friend. Always check if your answer makes sense, and significant figures show measurement precision. Practice makes perfect. Now, let's shift gears to one-dimensional kinematics, focusing on motion along a straight line. This lesson is designed for algebra-based physics students, providing foundational knowledge in college physics. By the end of this lesson, you'll be able to distinguish between scalar and vector quantities in motion, define position, displacement, velocity, and acceleration, apply kinematic equations to solve motion problems, and interpret position time and velocity time graphs. What is kinematics? It's the study of motion without considering forces. One-dimensional motion refers to motion along a straight line, analyzing relationships between position, velocity, and acceleration. It's the foundation for understanding complex motion using algebraic methods. Motion is relative to a reference frame. Choose an origin, establish positive and negative directions, and keep the coordinate system consistent. For example, on a highway, a car at mile marker 0 is at the origin, moving east is positive, and moving west is negative. Position refers to the location of an object relative to the origin. It has magnitude and directional sign, can be positive or negative, and is measured in units like meters, kilometers, or feet. The sign indicates direction, such as plus 15 meters right of origin or 8 meters left. Displacement is the change in position, not the total distance traveled. It's a vector quantity with magnitude and direction and can be positive, negative, or zero. For example, an object moves from one point to another, indicating its displacement. Average velocity is displacement divided by the time interval, a vector quantity with direction. It's measured in units like meters per second or kilometers per hour. Graphically, it's the slope of the position versus time graph. For instance, a car travels 100 meters east in 20 seconds, resulting in an average velocity of 5 meters per second east. Instantaneous velocity is the velocity at a specific instant in time, like what your speedometer shows. Graphically, it's the slope of the tangent to the position curve. For constant velocity, the average equals instantaneous, providing both speed and direction. Average acceleration is the change in velocity divided by the time interval, a vector quantity. It's measured in units like meters per second squared. Graphically, it's the slope of the velocity versus time graph. For example, a car accelerates from 10 to 25 meters per second in 5 seconds, resulting in an average acceleration of 3 meters per second squared. Instantaneous acceleration occurs at a specific instant, like the slope of the tangent to the velocity time curve. It's what you feel during sudden braking or acceleration. For constant acceleration, the average equals instantaneous, exemplified by the g-force in a vehicle or jolt from braking. Scalar quantities have magnitude only, while vector quantities have both magnitude and direction. Scalars are added using simple arithmetic, while vectors use vector methods. For example, distance and speed are scalars, while displacement and velocity are vectors. Let's look at an example of scalar versus vector analysis. A car travels 100 meters east, then 60 meters west, taking 80 seconds. Scalar analysis shows total distance and average speed, while vector analysis reveals net displacement and average velocity, highlighting the differences. Here's a summary of mathematical definitions. Displacement is the change in position, average velocity is displacement divided by time, and average acceleration is the change in velocity divided by time. Remember, delta means change in, crucial for understanding motion. Kinematic equations are essential for constant acceleration. Equation 1 links velocity, initial velocity, acceleration, and time, useful when displacement is unknown. Equation 2 links position, initial velocity, acceleration, and time, showing a quadratic relationship with time. In kinematics, we use specific equations for constant acceleration to link velocities, acceleration, and displacement. Equation 3 is particularly useful when time is unknown, while equation 4 employs the concept of average velocity, which is crucial for understanding motion under constant acceleration. Choosing the right kinematic equation involves a strategic approach. Start by counting your known variables, ensuring you have at least 3. Identify the single unknown, then select the equation that incorporates all knowns and the unknown. This method ensures you have exactly 3 knowns to solve for one unknown, streamlining the problem-solving process. Kinematics includes special cases like freefall, constant velocity, and starting from rest. In freefall, acceleration is due to gravity, while constant velocity implies no acceleration. Starting from rest simplifies calculations as the initial velocity is 0, making it easier to predict motion. A 6-step methodology can simplify problem-solving in kinematics. Begin by analyzing and understanding the situation, then draw a diagram and set a coordinate system. List knowns and unknowns. Select the appropriate equation. Solve symbolically. And finally, check your answer for reasonableness. Effective problem-solving in kinematics involves drawing accurate diagrams, organizing variables, and selecting the right equations. Ensure units are correct, magnitudes are reasonable, and signs make physical sense to avoid common pitfalls and achieve accurate results. Let's explore an example of constant acceleration from rest. A car accelerates at 2.5 meters per second squared for 8 seconds. By applying the appropriate kinematic equation, we find the car travels 80 meters, a reasonable distance for the given time and acceleration. Consider a ball thrown upward at 15 meters per second. To find its maximum height, we use the kinematic equation involving initial velocity and acceleration due to gravity. The ball reaches a height of 11.5 meters, demonstrating the effect of gravity on upward motion. Continuing with the ball example, we now calculate the time to reach maximum height. Using the velocity equation, we find it takes 1.53 seconds. This calculation confirms the time it takes for the ball to reach its peak before gravity pulls it back down. In this example, a car traveling at 25 meters per second brakes to a stop in 5 seconds. We calculate the braking distance using the average velocity equation, resulting in 62.5 meters. Additionally, we determine the car's acceleration during braking, which is negative due to deceleration. Kinematic graphs provide visual insights into motion. The slope of a position time graph indicates velocity, while the slope of a velocity time graph shows acceleration. The area under a velocity time graph represents displacement, helping us understand motion dynamics. In summary, one-dimensional kinematics involves understanding position, velocity, and acceleration. By following a structured problem-solving methodology, we can effectively analyze motion. Next, we'll explore two-dimensional motion and dynamics, expanding our understanding of kinematics.